or equal to sign on the calculator so you can check it?
Oh,
So you can check domain for that? I'm pretty sure there isn't, but I don't think there is. And there's no like imaginary numbers.
actually, I think there's a way to check it, but I'm not sure if it's on this old one. Okay.
They're on the newer calculators, right?
Yeah, like this one, I mean, you can type in the function.
I think it is in math. Second.
Math second.
Man, it's over here.
Oh yeah, it is, okay.
Second math.
Oh, second math, so it's test.
Second test. Oh, there we go.
See, you know stuff.
So what do you do?
It's, I don't know.
Oh, so you're checking,
Yeah. So it'd be like second,
you're checking the domain on, oh,
so you can go into Y and then you can go second test.
so if you want to check x divided by parentheses x squared minus 16, you put it there,
Oh,
or and then do second, or do you put it in your regular screen?
if you plot it, it just plots a straight line. Like if you graph it, if you graph like x less than or equal to 14, it just graphs a line. That's it.
Oh, this is, okay. Oh, it's in the square root one? So we want to check the domain of, which problem was that?
Oh, it was problem 20.
So we want to check the domain of 14, of square root of 14 minus x.
Yeah, I could have just.
So what happens if you just put, if you put in 14 minus x, second test, greater than or equal to 0? Oh,
It's just 1.
that doesn't work. Do we put it in y equals? Oh, because I didn't put the square root. Am I checking that?
Yeah.
Can you do test in here?
Yeah, you can.
What do I do, hit graph?
Yeah, you just hit graph. See, look, it's just a straight line.
Well,
Maybe your window.
that's because the window's not right.
Oh, really? Oh, okay.
You can change your.
The window, the answer is minus infinity to 14, so we only showing up to 10. So all of this is in the domain. Now we gotta change our window to make x go up to 20, and then let's see what happens. And it stops at 14, which count that.
Oh, yeah.
Okay, so I guess you can use your calculator.
Well, I wrote it wrong.
That's what
Yeah.
You read it backwards?
I wrote bracket 14 infinity.
Yeah. All right, so we are on section 2.3 and 2.6. You were supposed to do the self-paced Nearpod, and I'll check over the weekend, see if you did it. So if you forgot to do the self-paced Nearpod, 100-point classwork grade, go to nearpod.com, do IADSL, and we changed the due dates on these worksheets, but check and show me for due dates on worksheets. These were changed to Monday. Yeah, we changed them to Monday, but also 2.3 will be due Monday then. But I thought about having less worksheets since this is such a fast class, but it seems like since I don't collect the math lab work, I need to collect some work. And you need to get some feedback on some work. So you know, A, what do I want you to show, and B, you know, so I know if you're understanding it. So if you do it early and you want me to go ahead and grade it, I can grade it this weekend because I'm already regretting that I'm giving you till Monday. It's all right. Okay, so we're on section 2.3. But before we go to 2.3, was there any questions on 2.1? And I don't think I brought those notes, but did you guys get a chance to do that? Okay. Did 2.1 make a lot of sense?
Yeah, it did. I just had to double check on like the I squared turns into a negative 1.
Yeah, I squared equals negative 1. So you treat I like a variable, except when you get any I squared, you replace it with negative 1.
Yeah.
I is the square root of negative 1, and conjugates is the complex conjugate of A minus BI is A plus BI.
And if it's on the bottom, you just multiply it by top and bottom. By the
And if you're trying to divide 1 minus I divided by 4 plus 3I, to get a real number down here, you multiply by the complex conjugate of this. So you have to multiply by 4 minus 3I. And then, since you're multiplying the bottom by that, you're just changing the look of the fraction. You have to multiply the top by it. And this will always be, when you multiply you're going to FOIL this, you're going to FOIL the top, and on the bottom you should memorize that the bottom is going to be A squared plus B squared, where A is 4 and B is 3 here. If you multiply complex conjugates together, if you would FOIL it, the middle terms will cancel and you'll always get A squared plus B squared. It's always equal to that. So it's best just to memorize that for the denominator here, and then you're going to FOIL the top, and that's how you divide it. Does this go away? No, it's a real number. And then you're going to separate it and write it in A plus BI form. So if I were to work this whole thing out, I FOIL this, I get 4 minus 3I minus 4I plus 3I squared. That's my top. On the bottom, I'll have 4 squared plus 3 squared. This is all the work you have to show on it. This is negative 1. So you're going to get 4 minus 3, because that's minus 3 then, minus 7I over 16 plus 9 is 1 minus 7I over 25. And then you separate that to write it in A plus BI form. So that's the answer to 1 minus I divided by 4 plus 3I. That's just an example. That's the hardest thing about complex numbers, probably dividing. I mean, there's other tricky parts, I guess, but anyway, that's complex numbers. An example of dividing conjugates. Okay, well, we're going to go ahead and start section 2.3, and I don't have 2.3 filled with notes out. Oh, and I'll take roll, but I'll pause this while I take roll. Oh, I have, oh, what's the bonus?
Yo, when is it due?
Oh, it was due on the test day, but I'm gonna come up with another bonus. I'm gonna post it in Shogi.
Okay.
That's what I'm talking about. You always have the chance to do the math lab review before the test, and it's 5% bonus on the test. It's in math lab, and you should always do it, right?
It's worth it.
Right. But I'm going to post another bonus worth 6 to 10 points. I don't know how to figure that. But I don't have time to do it right this second. So it's going to be over the weekend. So be looking for it. I can send you a message and show me when I post it. And I'm going to write a note. Post test 2. I'm writing myself a note.
Thank you. I wrote myself.
Okay. I have to create it, so I haven't created it yet. Okay, and I am in. Okay, so we are working on section 2.3 now. This is test 3 material. We are right in the middle of it. And, where is Okay. Okay, so first thing we're going to talk about is this is polynomial functions and the graphs. And I do have a nice Nearpod for this, so I'm going to start that. This has nice things to make sure you're understanding the material. So Nearpod.
I made like a 76.
All right.
Yeah, I thought I did really good.
Maybe I should have less multiple choice if I'm going to make you show work.
I missed like the smallest things.
I might make less multiple
I didn't do
choice.
this last
Okay, my library. I want to see your work.
week. Just all of it.
So 17, and this is section 2.3. There it is. Okay, go to nearpod.com. This is going to help you understand this. ABEWV. Did you get, I wrote it up there. ABEWV. Go to nearpod.com and join it. Okay, so this is the definition of a polynomial function. We've got n is a non-negative integer. So the integers are minus dot 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 minus 3 minus 2 minus 1 0 1 2 dot dot dot. These are the integers. You gotta understand this definition. Oh, you can't see this. Okay, you can see that though. Let n be a non-negative integer. What do we mean by non-negative integer? Well, these are the integers, so n can be any of these. Okay? And we're going to let the coefficients of the variables be a sub n minus 1, dot 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 through a sub 0. And they have to be real numbers. And we can't let a be 0. And the function defined by this is called a polynomial function of degree n. The number a sub n, that's this number, is called the leading coefficient. A coefficient is just a big word for the number in front of the variable. So that's the definition of a polynomial function. So, you guys all got that written down? All right. And we have the filled in notes that you can be looking at too, but. So let's see if you understood that. Let's hide the student names. There we go. Okay, and let's not. This is what happens when I run it from here. Let's just. Oh, I'm going to go to New York. That's the problem with running it from there. I didn't want everybody to see each other's answers. Did you answer it? It doesn't take long. Is this a polynomial function or not? Is 7x to the 5th minus pi x to the 3rd, is that a polynomial function? Everybody should have answered that by now. So we're going to share it. So you can see that's just a poll, so I have to tell you the answer, right? So we're going to write on my paper 7x to the 5th minus pi x to the 3rd. 7x to the 5th minus pi x to the 3rd is, that was f of x equals, or whatever it could have been g of x. I don't know. Is that a polynomial function? What did you guys say? Yes. Did I give you degree? What's the degree?
Degree 5.
Right. That's the highest power. So what we're talking about is our n's all have to be non-negative integers. The exponents have to be non-negative integers. That means they can't be fractions. So the exponent can't be negative, and they can't be fractions. So that, and pi is a real number, the coefficients have to be real, pi is a real number, so this is a polynomial. Let's do the next example. No, I'm probably already. Here's the next one. Is this a polynomial function? 7x to the 3rd plus 2x squared plus 1 over x. And my filled-in notes aren't showing that. I didn't even write it down. What is it? What was it again? 7x to the 3rd? One over x, whatever it was, g of x, h of x, whatever else it was. Is this a polynomial? Go ahead and answer that. We're going to share that. And we have a lot of no answers. You should be just answering it. Okay, we're going to share it. So that's what people thought. It's 7x cubed plus 2x squared. And I don't remember the choices, guys, but because you can rewrite this as x to the minus 1, we have a negative, the answer is no. Because we have a negative exponent. So this little definition up there seems so easy until I start asking you, are these polynomials or these polynomials? And then you see that you've got to understand that exponents can't be negative and that you can rewrite 1 over x as x to the minus 1. So, and the next one is 7x to the 1/3 minus 4x squared plus 7. Was it 7x to the 1/3? I don't know, whatever it was. Whatever it was. Okay. Did you guys get that one? Oh, we're all over the place on that. We're going to share it? Okay. The x, it's not a polynomial. Oh, these are the answers. Okay. No is the answer. 25% of you got no. So that's why we have these little things. No, I mean, only 25% of you got that right. No, and it's because of the fraction. No, it has a fraction for an exponent. A fraction for an exponent. So, polynomials cannot have exponents that are negative, and they can't have fractions. So, that's what makes it a polynomial. Does that, those little holes help you understand the polynomial? Okay. And this is just all right. No more of those. So here's the next part, and I'll fill it in, or I'll make this small. We'll just keep coming back to it. So we're going to fill this in. Polynomial functions of degree 2 or higher have graphs that are smooth and continuous. And by smooth, we mean that the graphs contain only rounded curves with no sharp corners. And by continuous, we mean that the graphs have no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. So these are polynomials, but these are not. That has a break. This one has sharp corners. So is this function one of the common functions of algebra? Is that a polynomial?
No.
No, and I drew it over here with the... Yeah, it is not. That is not a polynomial. Sharp corners. And that's in the building notes too. So this is not a... Sharp corner, not a polynomial. Okay. And let's see if... All right. Make this big again. There's a definitions. Let's see, the leading coefficient test is next. But I have to fill this in. I think the slide for this next little part got put in the wrong place. So the behavior of the graph of a function to the far left or the far right is called its end behavior. In terms of end behavior, only the term of highest degree counts, as summarized by the leading coefficient test. So here's the leading coefficient test on your notes. And basically, we want to, n is our degree, n is the highest power exponent. So n is the degree. When n is odd, we have this situation. If a sub n is greater than 0, the leading term of x to the n, we have a to the n, x to the n, is the leading term. So if n is odd, you should think of x cubed, or f of x equals x cubed. And this is one of those graphs you should have memorized, and it looks like this, but we'll make a little box here. If n is odd and a sub n is greater than 0, that's this picture. We don't know what happens in the middle, but past the last 0 it's going to fall, and past the last 0 on the left and past the last 0 on the right is going to rise. So n behavior here, we're going to say it falls left, comma, rises right. That's this picture. We don't know what it's doing in the middle, but to the left of the leftmost 0 and to the right of the rightmost 0, to the left it's falling, to the right it's rising. That's its n behavior. If a sub n is less than 0, then we got to think of if a sub n less than 0, then you just put a minus sign instead in front of x cubed. Flip that about that's really a flip about the x-axis, but these flips on this would look the same. Flip the function, and we put like a little box. We're saying it rises left, falls right. So rises left, falls right. So to the left of our leftmost 0 it's rising, to the right of our rightmost 0 it's falling. And that's the picture. We don't know what it's doing in the middle from this n behavior test. This is the n behavior. So if I ask for n behavior, you'll say one of these 4 things. Rises left, rises right, falls left, falls right. So that was odd. It acts like x cubed. If a sub n is positive, but if a sub n is negative, then you flip that, and it's going to have opposite behavior. The book has a good thing on that. It says opposite behavior on the ends. And for n even, though, it's going to have the same behavior on the ends. They're talking about the ends. So it's either going to rise left, rise right, or fall left, fall right. And we think of x squared. That's for a sub n greater than 0. You guys know that's a parabola that looks like this. But we'll have a box in here. We don't know what's happening inside here. We're going to rise left, fall right. So rises left. Oh, rises right. Sorry. Same behavior. It's going to rise both ways. If you have a sub n less than 0, think of negative x squared. We just flip that about the x-axis. Well, we don't know what's happening in the middle here, but the end behavior is that it falls left, falls right. Okay, so that's just what we're getting at here is we're going to teach you how to make an approximate graph of these functions. So we're going to use the leading coefficient test to determine the end behavior of this graph. So we have x to the fourth minus 4x squared. But first, we look at the leading term. The leading term is x to the fourth. It has an understood coefficient of 1. So what's its degree? Its degree is 4. N is 4. That's even. So it's going to act like x squared in its end behavior. Our a sub n is positive. 1 is greater than 0. It's going to act like x squared. So, you're going to say for the end behavior that it rises left, rises right. Okay, so that's the end behavior, and I've forgotten about our little Nearpod here, so let's catch it up. In a second, people are still ready. So. I'll catch up with the Nearpod falling behind. Okay. All right, let's see what I've got here. Got those pictures, we talked about those, the leading coefficient example. So here, this is nice. They have a picture of the function. So now we can see it visually. Some of you guys said you were visual learners. That's the function. There's arrows. When it stops at the end of the graph, there's arrows. So there's arrows here. And so you can see past the leftmost 0 at -2, it's rising to the left. Past the rightmost 0 at 2, it's rising to the right. So that's the graph. The degree of the function is 4. The graph rises to the left and to the right. And so this is the graph. This is the slide that was supposed to got put in the wrong place. Moved around, okay? Okay, and then here's our next example. So we're going to put this example on the note. The nice thing about the slides is that it shows you pictures to go with this, and then I don't have to draw it. You could also graph it in your calculator to see it. So you can see that we were right about the end behavior. So we're going to use our leading coefficient test to determine the end behavior of this graph. This is in factored form. So your a sub n, so you need to find your leading term. We need to find our leading term. And there's a shortcut. You could FOIL this and then multiply everything through by 2x cubed. But we only need the leading term for this question. So the leading term will be 2x to the third, that's the highest power there, times the highest power of this binomial, x, times the highest power of this one, times another x. So our leading term, if we FOIL this all out, is 2x to the fifth. We don't actually have to FOIL it out. I think in the filled in notes I went ahead and foiled it out. And are you guys looking at the filled in notes? Yeah. So you do get that. This is a shortcut. You take your highest power and you can figure out what the leading term is without doing all that work of foiling. But, so here's our leading term. So our degree is 5, 3, n is 5, and our a sub n, our leading coefficient, is 2, and that's positive. So it acts like, since this is odd, 5 is an odd number, it acts like x cubed. And that's positive x cubed. So we draw the picture, and then we have a box in here. We don't know what it's doing in there, but the end behavior is that it falls left, rises right. Okay, and then the slideshow is going to show us the picture of that. Now you could also type that in your calculator, y equals, and graph it. But you're going to have to, in order to see it clearly, you're going to have to get the right scale on the graph to see it nicely. So, falls left, rises right. Everybody done? Okay. So we're going to, I don't have a picture of it. No. So let me bring the calculator up and let's try to get a picture of this. The calculator. Okay. Turn it on. Okay. Y equals 2x to the third times x minus 1 times x plus 5. And now if I just graph it, let's see, zoom 6, standard, zoom standard. Oh, that's helpful, right?
Yeah.
Okay. The problem is that we need to see a lot more. It is falling left, rising right. So let's make our y scale window. We got to make these polynomials. Let's make this negative 100 and positive 100, and then make the scale 10. Whoops.
Ooh, 0 would not be good.
0 would be good. Let's see what that looks like. And see, we're still not good enough to really, we're still not seeing the top of it. So, yeah, that's window. So we need to go up more. We have to go up to 1,000.
God bless. That's a lot.
And every 100. See, now we're not going to see the zeros clearly.
Yeah, probably not.
Yeah, but at least now you can see that it's falling left, rising right. We don't see exactly where it's crossing and what it's doing in there because now we made the scale so big. Okay, so that was to show you. So it's to pass our leftmost zero. Yeah.
What you drew over here, the calculator is different.
Drew and what the calculator drew is different? Really? What we're talking about here is the end behavior.
Yeah, okay, so like inside the square is like what we're looking at.
So
Yeah.
to the
That's why it doesn't look the same.
it doesn't look the same because I have an open square here. I don't know what's happening in between. We're talking about the end behavior. this is our leftmost zero or x-intercept. It's falling beyond that. That's what this is showing, falling. To our rightmost zero over here, it's rising. So this is discussing just the end behavior, and we didn't know what was happening in the middle here. So, no, this is not a complete graph here, it's just the end behavior.
Okay.
All right. Okay, so we're on the next page. So this is the definition of zeros of polynomial functions. If f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. These values of x are the roots or the solutions of the polynomial equation f of x equals 0. Now, when we talk about zeros, this is just the x value of, remember I always wanted ordered pairs, the x-intercept. Since I always wanted ordered pairs, zeros and the x value of the x-intercept are the same thing. Where is it crossing the x-axis? Those are called zeros. Why are they called zeros? Because when you cross the x-axis, y is 0. So that's why they're called zeros. It's because y equals 0 when you're on them. Okay? And they're also called the roots or solutions of the equation f of x equals 0. So if we set the polynomial function equal to 0, we can find the zeros. So we're going to find all the zeros of f of x equals x cubed plus 2x squared minus 4x minus 8. First example. So to find the zeros, we set f of x equal to 0. X cubed plus 2x squared minus 4x minus 8 equals 0. And then when you see if you see four terms in algebra, it usually works out that you want to factor by grouping. So we have four terms. Try factoring by grouping. Okay, so you're going to group the first two terms together and the second two terms together. And then you're going to find your greatest common factor of each one. So these two terms have the greatest common factor of x squared. You're going to factor that out. So x squared times what equals x cubed? X. Bring the plus sign down. X squared times 2x squared. What times x squared gives you 2x squared? 2. Distribute it again in your head to make sure it works. X squared times x is x cubed. X squared times 2 is 2x squared. And then, if there's a negative sign in front of your first term, you need to factor a negative out to make it positive. So we're going to factor, and the greatest common factor between 4x and 8 is 4. We're going to factor a negative 4 out. So what times negative 4 equals negative 4x? That's an x. What times negative 4 equals negative 8 plus 2? And this is still set to 0. Okay, so these match. And when they match, this is a common factor, even though it's a binomial. You can factor that out. So we're going to factor this out. We're going to be left with x squared minus 4. So
You got to set the each side to 0, the x plus 2 to 0 to find x.
no, we're not going to do that yet. We're still factoring.
Okay.
We will set it to 0. Look, we got a common factor here and here. We're going to factor those out. You put it out front, and you can think of another way to think of factoring is you're dividing this term by x plus 2. What are you left with? X squared. You're dividing this term by x plus 2. You're left with minus 4. And so I was still factoring. That's why I will set those to 0 in a minute. Okay? And then x squared minus 4 is the difference of perfect squares. You should memorize. We've got a difference of perfect squares. Should memorize this. You don't have it memorized, that a squared minus b squared always factors into a plus b times a minus b. That's called the difference of perfect squares. So here we have a difference of perfect squares. X squared minus 4 those are both perfect squares. So we bring the x plus 2 down, and we can factor x squared minus 4 into x plus 2 and x minus 2. So this factors Does everybody understand how we went from that to that? Okay? And then you could FOIL it and make sure it works, but the middle terms cancel and you're left with x squared minus 4. Okay. Now you're right. You're going to set the zeros. You're going to set the factors to 0. Well, you can write it one more time as x plus 2 squared times x minus 2 equals 0. So we're going up here. So now we're going to set our factors to 0. The only way this product would be 0 is if either factor equals 0. And so you get x equals negative 2 or x equals 2. So the zeros are negative 2 and 2. That's our zeros. So we found our zeros. Any questions? Did you follow all that? Yes.
Do you still want us to make them ordered pairs?
No, zeros are just the x value. So the zeros are just the x value. If I ask for intercepts, then I want the ordered pairs, and I'll say that in the directions. Because, Stat Lab or Math Lab is always asking just for the x coordinates. So, all right, so that's the zeros, and let's show you the slideshow if you're done writing. Are you done writing? Okay. The slideshow is going to show a picture of this. So they went through and did all this factoring too. So these slideshows are there. They're in Shobi. I just pulled them into Nearpod to add some. So they factored it, and you can also, instead of factoring, you can take the square root of both sides. If you take the square root of both sides, you have to remember your plus or minus sign though here. So we've got zeros of plus or minus 2. And that's actually two answers, -2 and +2. So you can also do this problem, instead of factoring, you can do it this way. Okay? And this is plenty of steps, what they're showing you here. I showed extra steps, because sometimes people need to see more steps, but there we go. Any questions? So that's the picture. That's it. Here's the picture. Except there's a typo on the picture and on some of the words here. All right. So I need to see, these are the old slides. I need to see if they fixed it on the new ones. The zeros are -2 and 2, but what's wrong with these ordered pairs? So they're drawing the x-intercept. The ordered pairs should be switched. X is -2, y would be 0 here. X is 2 here, y is 0. So they made a mistake, the publisher made a mistake here on these slides. But there's -2 and there's 2, and that's showing this graph. Okay, so we found the end behavior. Now we're talking about the behavior in the middle with the zeros. Okay? And now we have so I had to draw it in here. If you would like, or we can skip the draw and I'll just do the example. It's the next example, basically, isn't it? Find all the zeros of x. Yeah, it's the next example. But you probably don't want to draw on the computer, so. Okay, we'll write it on our notes. Okay?
It's gonna look like super sloppy if we do.
Yeah, let's not do that. And we don't want to spend the time doing it either. When I first started doing these, I used to put a lot of drawouts in there, and it just takes too much time. So, okay, so what are the steps to find the zeros of something like this? We set it to what?
0.
Right. So we set f of x equal to 0, and then we're going to factor. What kind of factor do you need to look for first?
You could factor out
Greatest, right, the greatest common factor of x squared. So if you first look for your GCF, greatest common factor. Good job. So you'll factor out an x squared, and you guys do that on your paper in a minute. Let's see if you can get that. Because if I do everything up here, yes. So I tell you the steps, yes. Set f of x to 0 and then factor, take out the greatest common factor. There you go. The draw, it tells you to do that, but you don't have to do it on there. Okay, so let's see. So we got x squared minus 6x plus 9. And then this factors into x and x. And what are the factors of 9 that add up to -6? Yeah. It's a perfect square trinomial. But you don't have to memorize those. Just look for the factors of c that add up to b. And then you can rewrite it as x squared and x minus 3 squared. So set x to 0 for the x squared, and set x minus 3 to 0, x equals 3. So the zeros are 0 and 3. Okay, then you guys, you probably got that, because so the zeros are 0, 3. So that factoring, it's really going to make this class much easier if you don't have factoring. I think most of you do. So, oh, look, somebody drew something. Hey, that's good. I can see that's factored, yeah. Okay, so we're going to talk about multiplicity.
Ew.
Like this, my knees.
So a multiplicity, so a multiplicity is how many times the 0 is repeated. So it really it doesn't tell you that here. A multiplicity is the number of times the 0 is repeated. Okay? So, this 0 right here had a multiplicity. Since it was an x squared term, it's repeated twice. So it's 2. The 3 was repeated twice. Look at the x one. So it's also 2. The multiplicity of these zeros were 2. What about up here? The minus 2 had a multiplicity of 2. But the x minus 2 term was only repeated once. Well, was not repeated. Only occurred one time, so it has a multiplicity of 1. And so our multiplicities of a 0 tells us whether the graph of the polynomial function touches the x-axis at the 0 and turns around, or if the graph crosses the x-axis at the 0. That's what the multiplicity can tell us. And so we can find out a lot about these graphs without actually putting it in our calculator and graphing it. So we're talking about if R is a 0, if R is a 0 of even multiplicity, it's used an even number of times, then the graph touches the x-axis and turns around at R. We're saying, what does it do at that 0? If R is a 0 of odd multiplicity, then the graph crosses the x-axis at R. And then regardless of whether the multiplicity of the 0 is even or odd, graphs tend to flatten out near zeros with a multiplicity greater than 1. So, now we're finding out about the middle part. So, another example, this is already factored. So, if it wasn't factored, you'd have to factor it. Find the zeros of minus 4 x plus a half quantity squared minus times x minus 5 cubed. So we're going to find those zeros, and it's already in factored form. So we're going to set f of x to 0. So minus 4 x plus a half squared x minus 5 to the third, set to 0. So we set our factor to 0. We can divide the negative 4 out. Goes away because it's just a constant. If it was a negative 4x, we could divide the negative 4 out, but not the x. We would have a 0 at x, but it's just a negative 4. So that doesn't affect it. That's negative 4 is not a 0. So we're going to set x plus a half equal to 0. We get x equals minus a half. Set x minus 5 equal to 0. We get x equals 5. So we have zeros at minus a half and 5. Now it says state, find the multiplicity of each zero. So let's make a chart. We're going to have our zeros, minus a half and 5. We're going to write down our multiplicities. And then we're going to state whether it crosses the x-axis. So it crosses the x-axis or touches and turns around. So minus 1/2 is used twice. And that's an even multiplicity. So it touches the x-axis at minus a half and turns around. 5, x is used 3 times. That's odd. So it crosses the x-axis at x equals 5.
I have a question.
Yeah.
So to find the multiplicity, whatever, use the exponents to do that?
Yes.
Okay.
You just look at the exponent. So this 2 made this 2, and this was the 3. So it's used 3 times. Right. So you got it. If it wasn't factored, you'd have to factor it. So that's what you use as the exponents when we factored it. Okay? Let's look back at our... So there's the example. So they factored, they set it to 0, and they told us in words to make it a little chart. And here's the picture. Look at the scale on the y-axis. 800. It's counting by 200s, and it's up at 800. So that's what we have to do in our calculator on these problems. You're going to see them. But so this has a 0 at minus a half. And the graph will touch the x-axis at x equals minus a half and turn around. So that's why it's turning around. And x equals 5 is odd multiplicity, so it crosses. And I'm not so worried about you showing it flattening out and things, but it does cross at 5. So you'll have to do sketches of these on the test, but... Any questions? So that's the picture. All right, so we have a quiz. So let's see if you guys get this. So I'm going to let you take the quiz. Maybe I'll take it too. Oh, I had scrap paper in my building book. It's time for a break, guys? Let's see. Well, let's take this quiz. Let's start it. Let's see. 2 tabs. A, B, E, W, W. So, you're taking the quiz. When you take the quiz, you can't hit the right arrow, you gotta hit let's go. I'm just gonna write it down so we can go over it. I skipped it. Question. What's the leading coefficient? If you skip it on the Nearpod I asked you to do, you're not going to get full participation, but you would answer it and hit submit. What are the zeros? The multiplicity is 0. Did you guys finish it? Still
Yep.
working? You did? Okay. This is 1 multiplicity. Okay. Okay. Submit. Oh, yeah. Okay. Let's see how I did. The one that got 0 out of 5 is me because I didn't answer any of them. But we're going to share this so you can see how you did. I think most people are done. You done? Now you can see how you did on this. So, and I can see the correct answers will be here in green. But it doesn't show you the polynomial function anymore. So that's the correct answers. Let's put it down here. These were the questions. So the hardest part of this is probably going to find that leading term. This is the leading term. You have to be able to find the leading term. And it would be an awful lot of work to FOIL this out and multiply this out and then multiply. You don't want to do that. So what you do is you take this part and then you take x, but because you're squaring it, the highest power you're going to get when you FOIL that is an x squared. And then you're going to, this is x to the 1, so you're going to take x. This is your leading term, minus 2x cubed times x squared times x. I'm not saying that this equals this. This is just the first term, the highest power term. And so you can find your leading term without FOILing it out. So once you get the leading term, you're going to get these. The degree right is 6. The leading coefficient is 2. That's the degree. And then you set these. You set this to 0. It's already factored form, so you're going to have a 0 of 0 and 1 and negative 5. Those are your zeros. And the 0 is used 3 times because it says x to the 3rd. the 1 is used twice because x minus 1 is squared, and the minus 5 is used once. Well, it didn't ask about that, but 1. And the behavior, if the multiplicity is odd, it crosses the x-axis at that 0, and if it's even, it touches and turns around. And if multiplicity of 1 means it's odd, it crosses the x-axis at -5. Okay? So, just a little, okay, I have to go back to where I'm controlling it. All right, so let's take a break. All right, this is the part, this slide is no longer in our notes. This is called the intermediate value theorem. Basically what it says, if there's a sign change, if f of a and f of b have opposite signs, and there's at least one value where you have a 0. So you look at sign changes, but this is, we're not really covering this. I had this in my notes and I took it out. We just never had time. But, so, if you've got a polynomial function, this is just an example of that if there's a sign change of f of x between -3 and -2, then you know that there's a 0 somewhere in between those two numbers. So if you put in -3 into the function, you get -42. Then you put in -2 in the function, you get -5. Let me draw a picture of that. It's just saying if you've got a function between -2 and it's up at -2, 5 here, and down here the function is at -3, -40 something. I don't know what it was, 42. If this function, it means there must be a 0. It's kind of common sense, maybe. So sometimes we have trouble finding the zeros. And this is just telling you, if you evaluate the function at -3 and you get a negative number, and at -2 and you get a positive, it must cross the x-axis, and there's a 0. That's what the intermediate value theorem is. We're going to go on to the, okay, there's a picture. So I drew it. It must cross the x-axis. That's not on the test. The intermediate value theorem is not on the test, and I took it out of the notes. Okay. So now we're going to talk about turning points. So the next page of your notes, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. But again, it doesn't say what are turning points. Turning points. What are turning points? That's where the graph goes from increasing to decreasing and vice versa. That's what a turning point is. So the number of turning points is at most n minus 1. So it's less than or equal to n minus 1. At most means less than or equal. So if you've drawn a graph and it's a degree 3, then it can only have 2 turning points at the most. Doesn't mean it has 2, it can only have 1. So, but anyway, this is the strategy for graphing polynomial functions. We're going to go ahead and do some graphs. We're going to use the leading coefficient test to determine the end behavior. We're going to find x-intercepts by setting f of x to 0. We're going to check out the multiplicities. That's in here. And, you know, the graph, if it's even or odd, even it touches, it turns around at the 0. If it's odd, multiplicity, it crosses the x-axis. And then we're going to find the y-intercept. We're going to use symmetry if applicable to help draw the graph. And then number 5, we're going to use the fact of the maximum number of turning points. So here it is. So we're going to put it all together in graphing this without typing it in our calculator. Okay? Why don't we just put it in a calculator? We can check it with a calculator. Okay? So we want to do the end behavior first. So let's find the leading term. So there's an x squared, and then there's x minus 3 squared. So the leading term will be x squared times x squared, or x to the 4th. There's a 1 there. So the end behavior, the degree n is 4. A sub n is greater than 0. That's our 1. So it acts like x squared. So it's going to rise to the left. It's going to have the same behavior. It rises left, rises right. That's the thing it might be multiple choice in the test for you. Rises left, rises right. This is the kind of thing, for work, you'd write something like this and write what the leading term was. All right, number 2, find the x-intercept. We're going to set f of x to 0, so x squared times x minus 3 squared equals 0. It's already factored. Set each factor to 0. X equals 0, or x minus 3 equals 0. So the zeros are are 0 and 3. The multiplicities, let's just make a chart here. The multiplicities of the zeros, they're both used 2 times because of squares, and that's even. So the behavior at the behavior at the zeros is that it touches and turns around. So I'll just write touches, okay? Let's find the one, and so what are the x-intercepts? Okay, the x-intercepts are 0, 0, and 3, 0. Number 3, find the y-intercept. That's where you put in 0 for x. That's f of 0 in function notation. 0 squared, 0 minus 3 squared. This is not 0. You're going to get negative 3 squared, positive 9. So our y-intercept is 0, 9. Step 4, use symmetry. Down to zeros. On number 4 about the symmetry. We can see if f of negative x equals f of x. That would be negative x squared times negative x minus 3. That's going to be a little harder to do. It's not. Turns out there's no symmetry. This was they're all. We could FOIL that out. We'd have to FOIL that out to check symmetry, wouldn't we? See, we have an x to the. Let me take some paper and FOIL that out. Check symmetry. X squared times x minus 3 squared. X minus 3 squared is x squared minus x plus 9. And x squared. That's x to the 4th minus 6x to the 3rd plus 9x squared. And we have even exponents and we have odd exponents. So it's neither even nor odd. Hi. Oh, hold on. Here, I'm positive. Okay. Neither, right there. So that's the symmetry, and then, so I'm letting you in this part. I don't make you do f of minus x and f minus f of x for symmetry. Look, if a function has all even exponents, it's going to be even. If it has all odd, it's going to be odd. But if it has both, it's going to be neither. That's the shortcut. Okay. So, and number 5, maximum number of turning points. So none, neither. Maximum number of turning points, n minus 1. What degree? 4. 4 minus 1 is 3. Okay, so now we're going to graph it. We put all that together and graph it. So, x-intercepts at 0, 0. Wait a minute. How did I mess up on this? 0? No, I did. Sorry, guys. Anything times 0 is 0. Just because I get a negative 3 here, I'm still multiplying it by 0. 0 times negative 3 squared is 0. If I got an x-intercept of 0, 0, I kind of have a y-intercept of 0, 0. That's the problem, sorry. I wasn't looking at my solution and I start going off, but... So our x-intercepts at 0, 0 and 3, 0, those are our two x-intercepts. Our y-intercept really doesn't help us because it's still at 0, 0. Now, our behavior is it rises left, rises right. So to the left of the leftmost 0, right here, it's going to rise. And it's actually, the scale on the y-axis is going to be wrong. You know, the scale on these ends up being really high because this is x to the 4th power. So these scales are, and then it's going to rise here to the right of the rightmost 0. It only has 2 zeros. That's the end behavior. It's going to rise to the left of the leftmost 0 and rise to the right of the rightmost 0. The x-intercept, we got that. The behavior at the zeros. At x equals 0, it's going to touch and turn around. So this is supposed to be smooth. It turns around, and we don't know how high it goes, but it must turn back around, and then it turns around at this 0. And I'm not interested in how high it goes, but do show a bump. Don't just show it too close to the x-axis where I can't see that you know there's a bump there. Sometimes that bump is very close to the x-axis. But, so that's the graph, just without using a calculator. That's the graph of this function. And I'm not interested in the y-axis so much. I want to see that you know there's a bump this way. It might have went like this. Okay. All right. So let's look back at the Nearpod. It goes through this. It determines the end behavior again. Is this the same function? -2, did I? Oh no, this is a different example. Okay, so this is a different example. That's weird. I didn't realize that was different. Okay. That's another example because it has an extra term in it. So it's going through the same thing, and this is posted. I wonder if I took that. No? Anyway, that's a different example. So find those. You can look back at that. And I could check that the degrees, the maximum turning points are 3. So look back at my graph. It goes from decreasing to increasing. That's 1 turning point. Increasing to decreasing 2. Decreasing to increasing 3. It has 3 turning points, and that's the most it can have. So we've done that graph. There's one more example. So again, and this one's not factored. So you're gonna. So you first, here's the function. You look at the end behavior. The end behavior, the leading term is x to the 3rd. The degree is 3. A sub n is 1, is greater than 0. So it acts like x cubed. So it falls left, rises right. Okay. Number 2, the x-intercepts, set it to 0, and refactor it. We take our greatest common factor out. X squared, x minus 3. So we set x to 0 and x minus 3 to 0. So we get x equals 0 and 3 again. So our zeros, make a little table here, our 0 and 3 are multiplicities. Look at how I factored it. For 0, it's 2, and that's even. So the behavior is it touches and turns around. At the 0. At 0. X equals 0. The multiplicity of x minus 3 is 1, and that's odd, so it crosses. All right, then the next thing is, and we can write the x-intercept as ordered pairs. It has the same x-intercepts as the last graph, but it won't look the same as the last graph. Number 3, find the y-intercept. Guess what? The y-intercept, if you put in 0 for f, you're going to get 0 in this function. It's 0 to the third minus 3 times 0 squared. 0. Anytime you have an x-intercept of 0, 0, you can get a y-intercept of 0, 0. And we have both even and odd exponents, so there's no symmetry. 5n minus 1 is 3 minus 1, so we have 2 turning points at the most. So if we get a graph that looks like it's making more than 2 turning points, we've done something wrong. So now we're going to graph it. Okay, so we mark the zeros are at 0. Are you done down there? 0 and 3. The end behavior is it falls this way. I don't know. And it rises this way. Falls left, rises right. And then what's it doing at the zeros? At this one it's touching, and so it means it's turning around. At this one it's crossing. Now, I'm not really showing that it's flattening out. That's okay. So that's the kind of graph I'm looking for. The numbers on the y-axis, they're not right. Okay. And I don't care how far down you show this little bump to go, except that I need to see which way it's going. So this is similar, this example is similar to the problem you have to do for homework in Shobi. So you guys, in Shobi, so we did that one, and then we'll get out of this near project. Reports. Okay. I'm gonna. If you guys in the Nearpod, if you want to send notes to yourself, you can. You choose notes, and you can email it to yourself or any of those options. Then I'll be getting out of it. Just want to show you Shobi. So don't forget to do the stuff in Shobi. It's worth 10% of your grade. And you need that to bump up test grade. So Shobi. So I've got the complex numbers quiz. Shouldn't be too hard. Show your work. Section 2.1 homework worksheet. Show your work. Section 2.3 on your own. Looks like this. Please change the scales on the x and y axis so I can see what's happening between the zeros. So, this problem, here it is. You got to factor that. You just tell me the degrees. Find the y and x intercept. Find the zeros. Write down the multiplicities. Say if it touches or crosses. Tell me the end behavior. It's one of those 4 things. Either falls left, rises right, rises left, falls right, or the other 2. So I want you to put 1 way over here, and then the y-axis scales may have to actually be, this might have to be 1 up here to see it. I need to see the bump in your graph. It's funny. Okay. All right. So, you can even just cross out the y-axis scales, and you're just showing me a sketch. The y-axis scales don't have to be there. But I want you to move 1 and 2 over because it's really hard for you to see. All right. And that's section 2, 3, right?